All right, this is the first video for section 4.3. This section is about increasing and decreasing, which has to do with the sign of the first derivative. And we're going to start by talking about that in with a little more rigor, maybe more formality than we have in the past. Because so far, we have talked about what it means for a function to be increasing, that, as you move from left to right, the function points go up, right? On the graph, it's increasing. And we've talked about how that correlates to having a positive derivative value, right? So positively sloping tangent lines. But in mathematics, we like to be very formal and very rigorous with the way we define things and the way we prove things. And so what I'm going to do is present to you this formal definition of increasing, alternatively decreasing, and then a theorem, the theorem that we already know about how the positive derivative value corresponds to an increasing function. And then we're going to prove that. So let's start with the formal definition here. We'll look at this. Increasing or decreasing. So decreasing is parenthetical in purple here. It says f is increasing. Let's ignore the purple for the moment, and then we'll come back and look at that. It says f is increasing on an interval a to b if for any x1 and x2 satisfying where a is less than x1, which is less than x2, which is less than b. So basically x1 and x2 are between a and b, and they're in order with x1 less than x2. Okay, so they come in that order. For any time you have x1 and x2 within this interval in that order, f of x1 is less than f of x2, which means basically the function value goes up, right? So the alternative would be to define decreasing by changing this definition just over here. So that instead of x1 is still less than x2, but instead of the function value going up, the function value goes down. So that's pretty straightforward. Now the theorem is if f prime of x is greater than 0 for all the x values on an interval, then f is increasing on that interval. Let's prove that. The first thing we want to do, whenever you're trying to prove a statement that says something like if A, then B, the first thing you want to do is just assume that your A is true. So in this case, A is the statement f prime of x is greater than 0 for all x in the interval A to B. So we're going to start by assuming that that is true. Now, given that assumption, we have to prove the following thing, right? So I'm going to write assume f prime of x is greater than 0 for all x in the interval A to B. This symbol right here is the symbol means is an element of. I think we've used this symbol before. So now we want to prove that f is increasing. And we're going to use this definition, right? This definition says it's increasing if anytime you have an x1 and an x2 in the interval that are in that order, x1 less than x2, then f of x1 is less than f of x2. So what we want to do is, suppose we have an x1 and an x2. We're not going to specify which numbers they are. We don't even know what a and b are, right? This is all very general. We're just going to suppose we have an x1 and x2 in this interval that satisfy that inequality. So I'm next going to write let x1 and x2, x1 comma x2, let those be numbers satisfying the inequality. A is less than x1, which in turn is less than x2, which in turn is less than b. So we're just talking about any two numbers that are between a and b, one less than the other. Next, we're going to invoke the mean value theorem. So I mentioned that the mean value theorem was important when in proving this theorem when I first introduced the mean value theorem. So we're going to use x1 and x2 as the two numbers for the mean value theorem. And the mean value theorem says that the average rate of change from x1 to x2 is equal to the instantaneous rate of change for some number in between x1 and x2. So by the mean value theorem, there exists a number c that's between x1 and x2, like that, such that f prime of c is equal to the average rate of change, which is f of x2 minus f of x1 all over x2 minus x1. That's the average rate of change. So now we get to use our assumption. Back here we assumed that f prime was positive for all x in a to b. Well, if c is between x1 and x2, and x1 and x2 are already in between a and b, then c must also be in between a and b, right? You can sandwich the c right in the middle of this inequality, and it's still in between a and b, right? So c counts as a number in the interval, and therefore we've assumed that its derivative is positive. So since c is in AB, f prime of c is greater than 0. F prime of c is positive. So now we're looking at this equation over here. I'm going to put a little box around this equation because we're going to focus on it. All right, this is the relationship between the derivative of f at c and the average rate of change between x1 and x2. The left-hand side of this equation is a positive number. We also know that the denominator of this fraction is a positive number, because if x1 is less than x2, then when I subtract in this order, x2 minus x1, that's going to be a positive number. And since we now know f of x2 minus f of x1 over x2 minus x1 is positive, because it's equal to f prime, and f prime is positive, and x2 minus x1 is positive, okay, if this whole thing is positive and the denominator is positive, well, we can conclude that the numerator has got to be positive, right? If the whole fraction is positive and has a positive denominator, it had better have a positive numerator as well, right? That we can conclude that. We know f of x2 minus f of x1 is greater than 0. Now all we need to do is add f of x1 to both sides of this inequality, and we'll say thus f of x2 is greater than f of x1, which, is that what I meant to say? Oh, which is exactly what I meant to say. It is written backwards, because over here I was trying to conclude that f of x1 is less than f of x2, right, in order to prove it's increasing. But this is the same statement, just written backwards. So maybe it would make more sense if we wrote it f of x1 less than f of x2. There we go. That's a little better. And therefore, I'm out of space, but therefore, f is increasing. And we proved it. So that's a pretty formal proof, right? We did some assumption of premises, and then we used a definition where we had to, again, assume something and then conclude something, right? This is the type of proving stuff that you do in proof type of things you do in like higher level math classes. And since this is calculus, you know, and you're moving towards higher level math classes, I wanted to take the opportunity to show you this proof in order to sort of introduce you to the type of thing that you will start to do as you move forwards. So if you're planning on going through and taking the whole calculus sequence and then taking things like linear algebra and differential equations, then you will end up writing this sort of proof on your own. And if you ever decide to take discrete mathematics, which is Math 2100, cross-listed as Computer Science 2100, with me at some point, if you ever decide to take that, then I will teach you a lot more about how to prove things and how to write your own proofs for theorems. Okay, and all the different strategies and the logic that's involved in that kind of thing. All right.